Okay, so let's talk about solving circuits, current, and the like. So let's go ahead and go through these examples in order to understand what's happening and be able to describe how current works and how it deals with resistance and potential. Now, number one, solve for the current through the 2 ohm resistor to the right. So I want you to notice that we have a battery with 6 volts of potential. Okay, that's our potential that we have. Okay, that's the potential to make the electrons want to flow. And now we have a resistor. Now, a resistor is something that resists the flow of electrons. It slows it down. This could be a lamp, this could be a fan, this could be whatever. But whatever it is that slows it down and oftentimes uses that slowdown to do some sort of work or action. So how would we find out the current? Well, it turns out that the current, or the I of the I of the current moving through, turns out that the current is going to be equal to the voltage divided by the resistance. Okay? So again, the current, that's the I, the current is equal to the voltage potential that we have divided by the resistance that we have to it. So the higher the potential, the higher the current is going through that circuit. The higher the resistor, the lower the current going through. Now in this case, it turns out it's just going to be 6 volts divided by 2 ohms, which is going to give us 3 amps. This is an ampere. Ampere. Now an ampere is the current. So let's go ahead and have that on there. 6 volts divided by 2 ohms gives us 3 amperes. And that's our current. Now let's say it's more difficult for the current to push through 2 3 ohm resistors as opposed to just 1. Now the question is, though, you've got 2 of these, how are we going to find the current going through it? Well, I want you to notice what type of current, what type of circuit is this? This is a series circuit. Okay? Because notice the current has to go through both of them to come out to the other side. And don't forget, current is going counterclockwise, but that's because the electrons are going clockwise. We talked about that with Benjamin Franklin earlier today. Now, what is the total resistance? Well, whenever you are looking at a current that is going in series through a circuit, then we are going to say that the equivalent resistor is adding up all of the resistances together. So in other words, there is a total resistance in the circuit, and the total, or the equivalent, is all of them added up. So it turns out that 3 ohms plus 3 ohms is the total, and we have a total of 6 ohms of resistance. So in other words, it would be the same as if we had the same design, but you only had one resistor that's 6 ohms. Okay? It's the same thing. Right? Now with that, we can then find that was the resistance, we can find the new current. Well, the current is now 6 volts divided by 6 ohms, which is 1 ampere. Alright, so notice, having more resistance slows down the current to now we're at 1 ampere. Now, what would the equivalent resistance and current for the circuit be if another 3 ohm resistor was added? Well, we know that the equivalent resistance would now be R1 plus R2 plus R3. So that'd be 3 plus 3 plus 3. And so the equivalent resistance would be 9 ohms. And we know that the current would be 6 volts divided by 9 ohms, which should be 2/3 of an ampere. Okay? Now, does the current flow through one resistor and then the next, or does the current flow through simultaneously through all resistors at once? Well, let me make sure that I explain this to you. Now, when you have electrons inside of a circuit, okay, what's important to notice is that all the electrons that are inside are actually all going to bump up against each other. So it's not the idea that, oh, well, you know, one electron flows super fast through here. No, that's not how that works. Instead, what we have is, imagine you have a whole layer of electrons, and there are like, you know, quadrillion, quintillion, there are all of these electrons, like tons of these electrons in there. Now, each one of those electrons then pushes up against another series of electrons, or in other words, all the electrons are bumping up the next electron. And then those will bump up against the next electron, and so on and so forth. So what's happening is that all the electrons in the circuit are all bumping up against each other at the same time. So it's not, the idea is not that you're going to have one electron moving. It's not as if you have one electron that's going to go all the way around, or even, sorry, the opposite direction. But anyways, point being, you're not just going to look at one electron moving through. In fact, it would take a ridiculously long time for those electrons to move through the circuit, because what it is that you have all of these electrons pushing the next ones, pushing the next ones, and then the next ones. So the whole circuit, all of them are moving at the same time. So they're all moving at the same time, all at once. And so therefore they're actually moving slowly, very slowly, but in large quantities, and simultaneously, all throughout the whole circuit. Okay? That's the idea. Okay, so now let's take a look at what happens when we have two different circuits. They both have 6 identical bulbs, but notice the right one has a short circuit. So in other words, the current can go around the light bulb instead of having to go through it. Okay, so with that, this is the idea that a short circuit means that a current goes through a different pathway. So for example, if you have a light and in your house and you have a short circuit, instead of the current going through the light, instead it might travel into the wall and go straight into the ground, you know. So things like that. A short circuit just means it's not traveling the intended direction. Now, in which circuit is the current greater? Well, remember, current is going to be voltage divided by resistance. Now they've got the same voltage, so that's fine. But notice in the right side, it's able to go around that light bulb, so it has a smaller resistance. So therefore, the right side is going to be the greater current because it has the smaller resistance. Okay. Now, in which circuit are all 3 bulbs equally bright? Well, notice we just said that the current can go around this particular light bulb here, so therefore they're not equally bright. So the left side, those are going to be equally bright because current equal through all 3. Okay? So that's what we've got there. Now, what bulbs are the brightest? So explain. Now notice, even though the current is still able to go through each of these bulbs the same way it did with the other one, there's going to be more voltage across each one. You see, on the left side, the voltage is being split up between all 3 of these bulbs. Okay? But the right side one, you're going to have a larger voltage over those there and a much smaller voltage in the middle. Okay, so that's because it's able to go around it. Not completely around it, but mostly around it. So the bulbs that are the brightest are the outside 2 on the right. Okay. And I want you to notice that the dimmest one is the inside one on the right. Now with that, okay, what bulbs have the largest voltage drops across them? So as we talked about, the voltage is not needed in that middle one very much. So therefore, we're going to say it's the outside 2 on the right because the middle one doesn't need as much of that voltage. In the circuit shown below, there's a voltage drop of 6 volts across each 2 ohm resistor. Now, remember what I said earlier. Remember how I said that when you had these in series, what we said is that you would add them up. So if you had 4.5 volts there, then you would add up the voltages across them. But it turns out that it's different when looking at parallel. So it turns out that in parallel, each one gets the same voltage drop across it. So not only would there be 6 volts going across this circuit here, there's also 6 volts going across this circuit here. So what we're saying is that, notice the voltage the current is separate for each of those 2 loops. So either it goes through the first one, like so, or it goes through the second one, like so. So each one can get that same voltage, 6 volts, 6 volts, 6 volts. Now, use Ohm's law to determine the current through each resistor. Now, what about trying to find out how much resistance there is? Okay, see, we don't know what the current is yet. Well, remember that before, when we looked at series, we said that if you just add up the resistances, then you get the total resistance. Well, it's different with parallel. So with parallel, now we're looking at 1 divided by the equivalent resistance is equal to 1 over the first resistance plus 1 over the second resistance. So let's see how that works. The first one was 2, the first one was 2, the second one was 2, so that makes 2 halves, which is just 1 whole, okay? Which means that if we were to flip over the R equivalent is the same as 1 ohm. Now this may seem strange. How is it that you add up the resistances and they end up with a smaller resistance? Well, that's because you're allowing the current to flow whichever direction is easiest. So it'd be sort of like if you had a bunch of cars in traffic and then you were to give them 2 different lanes to travel through. They're going to go much faster and easily. Okay? So now that we know that our equivalent resistance is 1 ohm, now let's find the current. So the current that we had total, okay, is the voltage divided by the resistance. Now we had 6 volts divided by 1 ohm, so that means our total current coming out of the battery is 6 amps. Now it's important to notice that this is saying how much is coming out of the battery. What we know then is that with each of those, we're going to actually split up the current between them. So let's look at the first one. Let's look at I1, okay? Notice you've got 6 volts divided by 2 ohms. So that first one's going to have 3 amps of current. What about our second one? Well, let's look at I2. Okay, so that's going to end up being another 6 volts divided by 2 ohms. Sorry. Here we go. Stop doing that. Okay, divided by 2 ohms. That's going to be 3 amps. So notice you're going to have 3 amps and 3 amps, which makes sense because it should add up to the total current. So remember before we said that the current would be the same going through the series? Well, it turns out for parallel, you add up the current and it equals your total. Now, what if the current through the battery, what is the current through the battery if it is the sum of the currents in the resistors? Okay, so we just saw that if you added them up, you would get 6 amps. Okay, which we can check, and we discovered that earlier. Now, fill in the current in the 8 blank spaces in the diagram of the same circuit shown above, again to the right. Okay, so we started off with 6 amps. Then we split between, let me just make that easier, sorry. Split between 3 and 3. Now those 3 amps continued along, but then they got rejoined by the original 3 that it had, and it went back to 6 amps again. Okay, and that's how we can see how the current connects with the voltage and resistance. Now, look at number 5. Cross out the circuit below that is not equivalent to the others. So what I want you to notice is this. This one has a parallel circuit here and here. The B has a parallel circuit here and here. Now I want you to notice this resistor is in the second loop just like this resistor. This one is in the first one just like this one. Now let's look at C. Well, here's a loop and here's a loop. So again, we've separated those two resistors. Okay? But now what I want you to notice is this. My first loop on D, I have one resistor, but my second loop goes through both. So that was why it was so different in the other three. The second loop didn't go through the second resistor. Sorry, the first resistor. Instead, it went around it. But in part D, it has to go through both resistors in that case. So this one's the one that's not going to be the same as the others. And finally, let's look at number 6. Consider the parallel circuit to the right. What is the voltage drop across each resistor? Okay, now let's understand first what we're looking at in regard to the circuit. This is a parallel circuit. Now remember we said before that when things are in series, you add up the voltage. However, in parallel, it's the same as the source. So we know that 6 volts, 6 volts, and 6 volts. Now, use Ohm's law to solve for the current through each resistor. So for my top one, that's going to be 6 volts divided by 2 ohms is 3 amps. Okay. Then, my next one, 6 volts over 2 ohms is 3 amps. My last one, 6 volts over 1 ohm is 6 amps. So what does that mean? That means that total, the current from the battery should be 3 amps plus 3 amps plus 6 amps should be equal to 12 amps. Right? Now, another way of looking at that, okay, so we're saying this is 12 amps. Now, if that's true, and we know it is true, okay, then it turns out that the current being voltage over resistance, we know that the resistance would therefore be the voltage over the current. So we know that the equivalent resistance for the circuit should be 6 volts over 12 amps, which should be half an ohm. Well, let's find that out for ourselves. We know that we've got 1 over 1 ohm plus 1 over 2 ohms plus 1 over 2 ohms. So altogether, that's actually going to be 2 halves. 2 halves plus 1. So that'd be 2 over 1 ohm. Okay. Now it turns out, therefore, if you flip it all, then you get 1/2 ohm as your equivalent resistance. So we end up finding out that that's correct. So go ahead and review this. Make sure that you understand the following things. Number 1, how are series and parallel different from each other? Okay. So how are series and parallel different? Okay. Second, how are you able to calculate the current, resistance, voltage for each type? Okay. And then finally, also being able to find the equivalent resistance for any circuit. All right. Thank you very much.